Artificial neural networks, or ANNs, are powerful computational models inspired by the human brain. They provide practical methods for learning a wide range of target functions, whether real-valued, discrete-valued, or even vector-valued. The idea behind ANNs is to mimic the way biological learning systems, like our brains, process information through complex webs of interconnected neurons. In the world of machine learning, ANNs have become essential for tasks involving complex data, such as images or sounds. This scene sets the stage for our journey into the fascinating world of neural networks, where we'll explore how these systems learn, adapt, and solve real-world problems. The study of artificial neural networks is deeply inspired by biology. Our brains are made up of billions of neurons, each forming thousands of connections with others. These neurons communicate information rapidly, enabling us to recognize scenes in a fraction of a second. This highly parallel and distributed computation forms the foundation of neural network design. By understanding how biological neurons process and transmit information, scientists have developed artificial models that can learn from data, adapt to new situations, and even outperform humans in certain tasks. This biological motivation is at the heart of why neural networks are so effective. Neural networks are composed of many neuron-like units, each acting as a threshold switch. These units are interconnected with weighted links, forming a highly parallel and distributed system. One of the most important features of neural networks is their ability to automatically tune these weights during learning. The input to a neural network can be high-dimensional, such as sensor data or images, allowing the network to process complex information. This architecture enables neural networks to handle noisy, incomplete, or ambiguous data, making them suitable for a wide range of applications. A classic example of neural networks in action is the ALVINN system, which learned to steer an autonomous vehicle on public highways. The input to this network was a grid of pixel intensities from a camera mounted on the vehicle. The network processed this visual data and outputted steering directions, allowing the vehicle to navigate safely. This real-world application demonstrates how neural networks can learn complex tasks directly from raw sensor data, adapting to changing environments and making real-time decisions. Neural networks represent data through layers of interconnected units. In the ALVINN example, the network's input layer received pixel data, which was then processed by hidden units. These hidden units computed weighted combinations of their inputs, and their outputs were passed to output units representing possible steering directions. The network learned to associate specific patterns in the input data with appropriate outputs by adjusting the weights during training. Visualizations of these weights can reveal which parts of the input are most influential for the network's decisions. Neural networks are particularly well suited for problems involving noisy, complex sensor data, such as images or audio. They excel when instances are described by many attribute-value pairs, and when the target output can be discrete, real-valued, or even a vector. Neural networks can handle errors in training data and are effective even when long training times are acceptable. They are ideal for situations where fast evaluation is needed after training, and where human interpretability of the learned function is not a priority. One of the earliest and simplest forms of artificial neural networks is the perceptron. A perceptron is a single-layer network that takes a vector of real-valued inputs, computes a linear combination, and outputs either 1 or -1 depending on whether the result exceeds a threshold. Each input is associated with a weight, and learning involves adjusting these weights to correctly classify training examples. The perceptron laid the groundwork for more complex neural architectures. Perceptron can represent decision boundaries as hyperplanes in high-dimensional space. It can model basic Boolean functions like AND, OR, NAND, and NOR, but it cannot represent functions like XOR, which are not linearly separable. For example, the perceptron can easily implement the AND function by assigning appropriate weights and thresholds. However, its inability to handle nonlinear relationships highlights the need for more complex network architectures. Training a perceptron involves finding a weight vector that correctly classifies all training examples. The process starts with random weights and iteratively updates them whenever the perceptron misclassifies an example. The learning rate controls how much the weights change at each step. This process continues until all examples are classified correctly, but only if the data is linearly separable. If not, the perceptron may fail to converge, highlighting a key limitation of this approach. When training examples are not linearly separable, the delta rule comes into play. This rule uses gradient descent to search for the best fit weights by minimizing the error between the network's output and the target values. The error surface is typically parabolic, with a single global minimum. Gradient descent starts with random weights and iteratively moves them in the direction that reduces error, continuing until the minimum is reached. This approach forms the basis for training more complex neural networks. Gradient descent works by calculating the direction of steepest descent on the error surface. At each step, the algorithm computes the gradient, which points in the direction of greatest error increase. By moving in the opposite direction, the weights are adjusted to reduce the error. The learning rate determines the step size, and the process repeats until the error is minimized. This method is widely used for training neural networks, but it can be slow and may get stuck in local minima. Stochastic gradient descent, SGD, is a variation of gradient descent where weights are updated after each training example, rather than after processing the entire dataset. This approach can speed up learning and sometimes helps avoid getting stuck in local minima. By making small incremental updates, SGD provides a good approximation to true gradient descent, especially when the learning rate is set appropriately. This method is widely used in training large neural networks. Overcome the limitations of single-layer networks, multi-layer networks were developed. The backpropagation algorithm enables these networks to learn complex nonlinear decision surfaces. For example, in speech recognition, a multi-layer network can distinguish between different vowel sounds based on spectral features. Backpropagation uses gradient descent to minimize the error across all output units, allowing the network to learn intricate patterns in the data. Key component of multi-layer networks is the sigmoid unit. Unlike the perceptron, which uses a hard threshold, the sigmoid unit applies a smooth, differentiable function to its inputs. This allows the network to compute continuous outputs and makes gradient-based learning possible. The sigmoid function maps any input to a value between 0 and 1, enabling the network to model probabilities and learn more complex relationships. Backpropagation algorithm trains multi-layer networks by propagating errors backward from the output layer to the hidden layers. It starts by initializing weights randomly, then for each training example, it computes the output, calculates the error, and updates the weights using gradient descent. Variations like adding momentum help the algorithm escape local minima and speed up convergence. Backpropagation is the backbone of modern deep learning, enabling networks to learn from vast amounts of data. Backpropagation is highly effective, it is not without challenges. The algorithm may converge to local minima rather than the global minimum, and training can be slow for large networks. However, multi-layer networks trained with backpropagation can represent a wide range of functions, from Boolean logic to continuous mappings. The ability to automatically discover useful hidden representations is a key strength, allowing neural networks to generalize well from data. Critical aspect of training neural networks is ensuring they generalize well to new data. If training continues too long, the network may overfit, memorizing noise or peculiarities in the training set rather than learning general patterns. Monitoring performance on a separate validation set helps detect overfitting. The goal is to find a balance where the network performs well on both training and unseen data, ensuring robust and reliable predictions.